And the statement for this example says determine, pretty straightforward, determine the forces, let's say, in each member of the truss, just for the sake of completeness. And also indicate whether the member or the members, let's just put them all together, members are in tension or compression. Right. So we are going to follow the note I mentioned, that we look at each joint. We have to make sure that the joint we want to use, to isolate that joint and look at its free body diagram to find whatever force, external or internal force we're looking for. We have to make sure that joint meets those requirements. What were those requirements? Go back. We have to start from a joint that have at least one known force and at most two unknown forces. So let's take a look at these joints. Let's start with joint B there. I have one known force. It's good. I know 400 newtons is applied as an external force. But if I isolate this, I'm going to have one force in this direction, another force in this direction, another force in this direction. So that's not going to work, right? I have three unknown forces there. I don't know these internal forces in these members. So that's not going to work. Let's take a look at joint D there. If I isolate this one, I have an external force. This is a known force, so it's good. I have one known force, at least. Let's see how many unknown forces do I have. If I isolate this, right, the internal forces would be this one, and this one in this direction. So again, at joint D, I'm going to have three unknown forces. So that's not going to work. I have to have at most two unknown forces. That's also out. Looking at joint C, right? This point C, joint C, is where the structure, or this truss in this case, is attached to some support. What kind of support is that? Can you tell me based on the way it looks? It is a pin, yes. So it's a pin support. If you remember when we were talking about rigid body, equilibrium of rigid bodies in two-dimensional space, right? We talked about different types of supports. Remember, we were talking about cantilever beam, we were talking about roller, we were talking about pin beam, pin supports, and we said if we isolate them or if we remove them from the structure, how many forces do we need to replace those supports in two-dimensional space? So if I want to isolate this, I have one internal force here, and I have one internal force here. Now, since I'm isolating this, right, so obviously I have to get rid of the support as well. So if I put point C here, I'm going to have one force there, one force here. I don't get into the direct detail of direction. Let's say the directions are in this way, for the sake of this argument. Now, since this is a pin support, and I'm isolating that just pin, and I'm taking that point out, I have to replace that support. And so since it's pin support, I have to replace it with two more forces. Replace that support with two more forces. So I'm going to end up having a point or a particle like C, which is in this case a joint in my truss, with four unknown forces. Well, that's not going to work either. I don't know the support reactions, and I don't know the internal forces. Keep in mind, the support reactions for us, this case, would be external forces. when we're talking about the structure, we said we can either have external forces, internal forces. Internal forces are the forces between members. External forces are the forces that are applied to the structure, or the support forces, support reactions. All right, so that's not going to work either. Let's take a look at joint joint A. Here, C didn't work. I have a picture. Now, joint C is also a support, is a point that is exactly on a support on my truss structure. Now, what type of support is that? If you look at it, can you guess based on the shape? It's a roller, right? It's you can think about this as a contact, smooth contact even, but it's a roller. So that would be, if I want to isolate this, when I take it here, this is point A, I have my internal forces. This one, let's say in this direction, doesn't matter at the moment. No, that's the wrong direction. Obviously this direction, right? Direction along the member. These are internal forces. I'm going to have also one external force here, which is the support reaction. So now point A is a point with no known force. I don't know any of these forces. And 3 unknown forces. So that also does not meet the requirement, right? We said we need to have at least 1 known force and at most 2 unknown forces. So this is not going to work either. At this point, I ran out of options. Right? So what do? There is no joint that I can actually go with or start my process with, because none of these joints meet that requirements. So they're not useful. So what do I do now? So we're going to use what we learned before, right? About rigid bodies in 2-dimensional space. I don't know what you mean by except the minus 15. I see what you did there. All right. All right. So what we do is we're going to look at this truss, right, as the whole rigid body. If you look at this just as one rigid body, right, this is structure, it's the rigid body itself, right? Let's draw. Let me try to draw it here. Something much nicer than this. But if we just look at this as a whole rigid body, go back to what we learned when we were talking about rigid body, equilibrium of rigid bodies in 2-dimensional space. If this whole thing is a rigid body, and we do not consider internal forces, just do not dismantle joints and members, pretty much here is what we have. We have a rigid body that has one force applied here, another force applied there. Then we have some support there and here. So now we can use what we learned in equilibrium of rigid bodies in 2-dimensional space to find these support reactions. Once we know these support reactions, we can use those and start looking and using method of joints. Because once we know the support reactions, we start seeing joints with enough or joints that can meet that requirement. If I can find this support reaction here, then joint A is going to meet the requirement. I'm going to have 2 internal unknown forces and 1 external known force. So I can actually start from joint A. Or let me see, even if I find these 2 support reactions, right? If I find this force here and this force there from my rigid body, then point C also is going to meet the requirement, because I'm going to end up having 2 known forces. I said I need at least 1 known force. So I'm going to have 2 known forces, reactions, and I'll have 2 internal unknown forces, which is fine because I can have at most 2 unknown forces. So situations like these, instead of starting from the joint, if we cannot find any joint that meet those requirements, right, we draw the free body diagram for the whole truss and use what we learned from equilibrium of rigid bodies in two-dimensional space to find these forces, reactions. So let me write it here as a note, so you know why did we do that. None of these joints has, let's put it this way, at least one known force and at most two unknown forces, which we saw. We went over each joint one by one. We went over these joints one by one. So we look at the free body diagram of the whole structure and try to find, let's say, support forces. So that's what we're going to do. All right, let me draw a better truss there. Go, I'll draw it like this. It's a little better at least. And let's connect this. All right. Supposed to be straight. As straight as I could make it. There you go. All right, so the forces, I already told you those forces. I'm just going to put those forces here. I have one roller there, so just one force perpendicular to the surface. I have a pin joint there, or pin support there. So I put it there and there. Well, let's just, I'm going to put it this way. It doesn't really matter which direction when it comes to support. I have external forces there. One there, another one there. There you go. So let's put the name CX, CY, AY. Remember, when we're dealing with support reactions, we have some freedom to decide which direction. If the direction is not correct, we're going to end up getting a negative value. 600 newtons. You can always use the inspection and have some guesses, but which is good. So you go with those guesses. But if it turns out to be wrong, usually what happens is that you get the negative value. All right. So let's do what we were doing. All right. When we're looking at equilibrium of rigid bodies in two-dimensional space, we said we have summation of forces, vector sum of all the forces should be 0. Right? Does that mean? It means summation of forces in x direction should be 0, and summation of forces in y direction should be 0. What do we have in x direction? And let's take this as positive and this as positive, so we don't get lost. So what do we have there for these two? 600 minus Cx, exactly. 600 minus Cx, and that's pretty much it. So from here I can get Cx would be 600 Newton. We have Ay minus, that's correct, Ay, thank you, minus Cy minus 100 in y direction, which from there we'll get Ay minus Cy is equal to 400. Let me follow the typical color code that I do. So this would be Cx. Now we get this one there. Now we have one equation, two unknown. What are we going to do next? How can we find Ay and Cy? We use moment, right? Somebody's on fire. So we use moment, summation of moments. Which point I have to find the moment about? C, exactly. Thank you, guys. That made me happy. So point C, right? Because we have Cy as an unknown. We could go with point A, 2, because at this point we know Cx. So both point C and point A have just one unknown. But if we didn't know Cx already, definitely point C would have been the best option. And it still is one of the options. Let's go with point C. As always, I take counterclockwise as positive. Summation of moments should be 0. So let's see, what do we have? Finding moments about C. So what components do I have and what are the distances? You know, considering the dimensions you have on the truss structure. Give me some answers. Waiting. So we're finding a moment about point C. Counterclockwise is the positive direction. So we have 600 times 4. Yes, thank you, Elizabeth. 600 times 4. Right. The component, the force vectors, 600 external force. My 4 fingers along the direction of the force, the palm of my hand facing the point I'm finding a moment about. That would be the direction, but I make a fist, right? So it's counterclockwise positive, and the distance would be the length of the member CD, which is 4 meters. Right? So 600 times 4 is positive. What else? 400 times 3, exactly, plus 400 times 3. Well, we have the external force 400, 4 fingers along the line of action, right? The same direction as the force, the palm of my hand towards the point I'm finding a moment about, make a fist, right? Try to make a fist. 4 fingers, they're going in counterclockwise, so the moment would be positive. 400 times the distance that point has, the line of action, the perpendicular distance between the line of action for 400 newtons and point C, which would be the length of the member BC, and it's 3 meters. So 400 times 3. Anything else? So we took care of 600, find its moment about point C. We took care of 400, these two external forces. What else is there that we haven't considered yet? Yes, minus AY, well, square root of 52, I don't know where to get that. But since AY is in this direction, pay attention to the line of action. Right? This is the line of action, right? Yeah, yes, Sama. It would be 6. Right? This is the line of action, and I'm finding a moment about C. So the perpendicular distance between this line of action and point C would be this distance. And how long is this distance? Yes, so it's going to be 6. 3 plus 3. So that would be AY times 6. And the sign, well, AY is this way, so 4 fingers, palm of my hand towards the point C, making a fist. My 4 fingers are going in clockwise direction, so that would be negative. That becomes negative. That would be 0. So from here, you can actually find AY. And AY would be 600, if I didn't make any mistake. This would be AY. Now that we have AY, we can go back to this equation and find CY. All right, so as a result, CY becomes 600 minus 400, 200 newtons. Now we are in good shape. Now we have a truss structure that we know its support reactions. So we can start from any point, not any point, but oops, that was not supposed to. Let me clean this up. So we can start from any. We can take a look again at these joints. Right? Let's take a look at joint A. At joint A, if I isolate that joint, well, I have this AY that I know its value now is 600. Right, so let me go to next page. Now let's look at, let me put some few words here. Now let's look at joint A. And let's say this is joint A. I have my AY there. Let's put AY is equal to 600 newtons. I have to figure out the internal forces. Well, I know their line of action. We said the challenge would be guessing the direction, whether that member is under tension or compression. And we said we can afford having one unknown direction, but we have to use inspection to figure out at least the other one, or one of the unknowns directions. Now, in this case, let's go with member AB, right? 400 Newton is pushing it downward, and it's fixed there at point A. Can't go down. It can only go this way. So what happens is that if we have this one downward and this one cannot go down, what ends up happening is that this member AB is under compression. If it's under compression, it means it's applying a force in this direction to joint A. I'll call this FAB. The other member, it's not that easy to figure out. AB can be under tension, can be under compression, depending on what is going on there. I'll just I'll just put it in this direction. We'll see what happens. I know AB is under compression, so this one, I'll just leave it in this direction, just some guess. And I'll call it FAD since it's connecting A to D. All right. Now let's take a look at what we have here. Remember, this is joint A. Now this is equilibrium of a particle in two-dimensional space. I need to find, well, summation of forces should be 0 for this particle. Can afford one unknown direction. So yes, we are basically. Is that always the case? Yes, that's always the case. We can afford having, as long as we know the correct direction. It's a good point. If we have more than 3 forces,
So
as
like
long
if you
as
have,
sorry,
yeah, go
go
ahead.
ahead.
So if you have like, say like 4 forces on point A,
Mm-hmm.
would you still only afford to have one unknown direction, or would it be like two? You know what I mean?
Yes, I know what you're talking about. So uh, we have 2 equations, right, for a particle, equilibrium of particle. Right? So what we can afford, let me actually think about this. I'm not going to answer this question because I have to look at a couple of cases, might be case by case. What I have in mind is always a joint with 3 forces. That's a pretty good question. I'll get back to you in next class. I do not want to give you an answer that might be, you know,
It's
not.
okay. I mean, as if all the questions we're gonna do, or like most of the questions we're gonna do, is gonna be having like 3 forces, then
Well, as a
you
matter
know.
of fact, that's not the case. You might have more than. Let's go
Oh,
through
okay.
this example.
All right. Okay, that's
Let's see
fine.
if we can get something out of it along that line. It's a good question, though. I have to. So let's say summation of forces in x direction is 0, summation of forces in y direction is 0. Right? And let's take this as the positive direction is positive direction. All right. So as some of you might have guessed, I need to have this angle there to be able to find the components of FAB in X and Y directions. Now, what is that angle? If I go back to its structure, if you look at this angle theta there, I can, well, one way you can do is that theta is equal to tan inverse what we have in the opposite, which is 4 meters, what we have as adjacent, which is 3. So 4 over 3. I can get the theta, tan inverse 4 over 3 is, occurs a lot, so I could actually know that, 53.13 degrees. If you did not figure out, if you did not follow what I did, let me know. This is a right triangle there. Right. So we are finding theta in this right triangle. Whatever is opposite over whatever is adjacent, tan inverse of that fraction. All right, so if I know that, this gives me minus FAD. I took this as, so yeah, plus, well, minus, let me see, minus FAD minus FAB cosine theta is equal to 0. And correctly, right? Yes. And AY, or minus FAB sine theta plus AY is equal to 0. So from there, let's see what we get. We get FAB as AY divided by sine theta. Hopefully I did the calculation. Yes, I did. Is 750, if I did not make any mistake. And from the first equation, FAD becomes minus FAB cosine theta. So FAD becomes minus 450. What does that mean? This means that this negative I got here, this means that I took the wrong direction for FAD. So the actual direction should be in this direction, FAD. What does that mean for the member AD? Can someone tell me that? For the member AD, is the member under tension or compression now that we know the direction of FAD? Yes, it's under tension, right? Because once we have a member under tension, right, think about exactly. So if you have a member under tension, the force on the member is trying to, let's say, elongate the member. And since the support or the joint is stopping that, or is trying to stop that from happening, it's applying a force in opposite direction equal, right? Newton's third law. So FAD would be in this direction on the joint, the green arrow I put there. This means that this member AD is under tension. So far, we got two members, one of them by inspection, the other one, the direction of force in each member, or whether that member is under tension or compression. We got it, one of them by inspection, the other one, we figured it out from the free body diagram. Right. Let's now go to another joint. Let's go to this joint, joint C. All right, let's do this one. Let's isolate this. Let me switch the direction. If do we still keep the negative or do we turn it to positive number? So we either do the rest of the calculation with the same direction and plug in FAD as negative number whenever we face FAD, or we flip this direction in free body diagram, use the positive FAD. So if we keep the direction the same, always plug in minus 450 newtons. If you flip the direction, if you keep the direction the way it is, always use the negative 450. If you flip the direction, change this number to positive 450 for the rest of your calculations. All right. Let's look at joint C, which is a member with 4 forces. This is joint C. Let me put it here. And let's do it. What did I do there? Let's just do the same thing. Cx and Cy, the directions were correct. So these are Cx, external forces, Cy, and I know their value now, Cx, Cy. Cx would be, or it was 600, Cy 200. So this would be 600 newtons, this is 200 newtons, and I'm sure about the directions because that's what I got from freeway diagram. All right. Now let's look at the other forces. Let's look at BC and see what can we get from that. BC and CD. Now, these two, let me see how I can explain that. So if we have member, let's say CD, fixed there, and we are pulling in this direction, let's see if I can find a better way to explain this. Actually, I'll get to you guys. Do you think BC and CD are under tension or compression? Do you have any guess with some reasonable explanation that you can give us? CD would be under tension. So if this is C and this is D, we're pulling it this way. So your logic would be, well, CD, the length is going to increase. Right? So you say CD is under tension. If it's under tension, we are going to pull it this way. So what would be the direction of the force on point C? Upwards. There you go. But if it's under tension, the direction should be downward. So if I go with your assumption, this would be the direction. Am I correct? And let's say the other member, let's go with the same assumption this way. Let's say it's under tension, we go with the same assumption. And now what is the problem here? The problem would be, by looking at this, I guess we can figure out that since we established the direction for Cx and Cy, go back, let me call these so I can refer to them. This would be FBC or CB, and this would be FCD. They don't cancel out, exactly, right? If I sum up the forces in X direction or Y direction, we're going to end up having a negative value for FCD and negative value for FBC because they're not canceling out. We have a static equilibrium. So I have to flip both of them. So I have to say these are under compression. So I guess that's a good assumption with the point with 4 forces. Again, it goes back to inspection. You could assume, let's say, what could be the other assumption? The other assumption would have been this is in this way. One of them is under tension, CD under tension, BC under compression. Then we would have found BC is correct, the direction, but CD is not correct, and we had to flip it. So in order to get something that forces cancel each other out, and we have equilibrium in 2-dimensional space, we have no other option but considering BC and CD under compression. Well, let me just flip this. So If we have actually 4 forces, probably it's not as straightforward as I was putting it. We can afford one unknown. We actually have to look at it case by case, and we have to do some inspection. In this case, I would say that was hopefully everyone followed what I did there. Right? I'll put this FCD and FCB. Any other assumption for these directions would have given you negative values for FCB and FCD, and you had to flip them. Right? Hopefully you followed. So let's just do it here. Summation of forces is equal to 0 for this case. Let me be more intelligent and separate these. This is joint A. This is joint C. So what happens there is summation of forces in X direction would be 0, positive. Summation of forces in Y direction would be 0, upward positive. From the first one, you will get minus 600, which is Cx, plus FCB is equal to 0. For the second one, you will get minus 200 plus FCD is equal to 0. So from the first one, you'll get FCB is 600 and FCD is 200 newtons. You could get a different direction for each of these, but then you would have ended up getting a negative value, meaning that your assumption was wrong and you had to fill it. Hopefully everyone followed that part. So yes, to answer your question, Samuel, is that it's not as straightforward when you have more than 3 forces, I would say. Affording one unknown direction is only the case when we have 3 forces. Other than that, you actually have to play around with directions. That would be the most, I would say, from my experience, would be the most challenging part when you're dealing with trusses and using methods of joints. That to get the right direction. By the end, you will get all the right directions, right? But in so many cases, you might end up flipping the directions and use some logic to make sure that, well, this is in equilibrium, so they have to cancel out. All right. I know it's not as nice as just having one rule. That's all we got. All right, joint D. Let's go for the last joint here. I'm going to isolate this one. Let me go to joint D there and put D, let's say, this is, what color do I use? Green. So let's say this is joint D. Where should I put it? Considering the directions, let's put it here, D. We have the external force, right? We had it in this direction. To check the number. We had the force FDA and the member from FBD and FCD. So let's see what we got and use. Well, FCD we know is under compression. All right, so I'm just going to put it here. This would be FCD. And this is my 600 newtons. Going to FAD, well, we figured out the right direction of FAD is the green, meaning that FAD is under tension. Now, since FAD is under tension, you either go with the direction that you assumed for compression and use FAD negative, or go with the direction for tension and consider it as positive. So I'm just going to go with the correct direction, what we got at the end, right? This direction. We said that should be the correct direction for FAD, meaning that member AD is under tension. Right? So if it's under tension, right, I have to put it this way. There you go. Again, think about it. Under tension, the force, the joint is trying to avoid or stop the member from elongating. Right? So it has to cancel the force in the member. In that member, this is the force in the member. Oops. want to make sure that everybody follows this. Now, this is the force in the member. This is the member AD. It's under tension, so this is the force. Now, at the joint D, we have to put the force with the same magnitude, opposite direction, if it's under tension. So that would be my FAD or FDA. Hopefully that makes sense. Always think about the member, see if it's under tension or compression, flip that force, put it on that joint, that connecting, that member to that joint. And FBD, I actually cannot tell it's under tension or compression. So I'm going to assume it's under compression. Right? Everything else I know for sure. I found the direction and values for each force on this joint. So I'll just assume that it's under compression. Definitely I can afford one unknown direction if I have 4 forces. For 3 I can, definitely for 4 I can. So F BD. A little crowded there. But we have the values for all of these. FCD we found to be 200 newtons. So I'll put it here. FAD I found to be, did we find FAD? We did somewhere, 450. And since I'm putting in with the right direction, I'll just put positive, 450. And what else? That's pretty much it. All right. This is the angle I have here, theta. What is the angle theta? Go back to the truss structure. Look at this angle there. It's the same as the other theta. You can find tan inverse for, if AD is 450 and it is less than 60 newton for the force at D, can we assume FBD to go the other way or no? Yes, you can. And you will see that we are going to end up finding a negative value for FAD because of the wrong assumption you're making. Right? But I assume that I don't know, and just let's say it's just unknown direction. So theta is the same value, 53.13 degrees. All right. So let's go with summation of forces is equal to 0. In this case, I can actually just use summation of forces in x direction. I don't even need the y direction. Is equal to 0. Let's see what we got there. We have 600, positive, obviously, minus 450, which is FAD, plus FBD cosine theta, and that's pretty much it. It's equal to 0. So from there, I can find FBD would be 600 minus 450 goes to the other side, obviously becomes negative, divided by cosine theta. I think we're going to get minus 250 newton. So I got a negative value. As you said, Richard, you pretty much figured it out by looking, but assume that we don't know. So this means direction we assumed is not correct. And it should be, I would say, flipped, or the force should be flipped. Now, if we flip it, what does that mean for member BD? Is it under tension or compression now? Well, at this form, it's, I show you that it's true. So it's going to be under, well, if this was the force, we would have had compression. Keep in mind again the member, right? I know this is confusing. So if we have member BD, oops, I am running out of time there. But just 5 more minutes, folks. We'll wrap this up. So BD, if it's under compression, these are the force on the member. So the force on point or joint D should be in this direction. And this is BD. But what we end up having was this. We said, well, the direction should be flipped. So member BD is now under tension because the force is in this direction at point D. This is compression. This is tension. So when the member BD is under tension, the direction of the force FBD would be in this direction. If the direction I assumed at the beginning was correct, yes, the member was under compression. But since I had to flip the direction, this tells me that the member BD is under tension. This is something that you have to practice and keep practicing, thinking about the member, it's under tension or compression, flip that force and put it on the joint. Now, if the joint has that specific direction, the force, and you have the force on that specific direction, go in the opposite direction. Flip the force, put it on the member, and see if the member is under tension or compression. It's just going to take some time to get used to this. We only have two options, but it still can be confusing because we have too many members. Does that make sense, guys, now, of what we did there? I hope it does. Silence is usually good, but not in this case. All right. So, I know you want me to wrap it up. So I'm going to wrap it up. We got all the forces we wanted, and we figured out all the members. So I'm just going to put it briefly here. What members we had? A, B, A, let's say D, BD, and what did we have? AB, AD, BD, AB, AD, BD, BC, and CD. BC and CD. Now, I just want to give you some summary of they were under tension or compression. So this member, AB, what did we found about AB? We found AB is under compression. So when later on, when you look at this, you can check your interpretation with what the final status was for that member. AD was under tension. BD ended up being under tension. BC, I have to look at BC. Do we have it here? No, I have to look at BC. BC ended up being in compression. And eventually CD ended up being in tension. So use that for reference. We went through each joint one by one, and we were trying to figure out, so let me double check, AB, hopefully we got everything was right. AB was under compression, BD under tension, AD under tension, BC under compression, and CD under tension. One is missing. CD, actually CD is this one. Yeah, we found CD under, even I'm lost at this point, just going back and forth these slides. We found CD to be under compression, sorry. Yeah, that's the direction of CD here we have on this one. So CD is under compression. Just gonna correct this. CD under compression. Oops, that's what happens when I want to fast. Compression. All right.